So yeah, so today this is this is not lecture information, this is for benefit. Today we'll cover some definitions, like a few in the first part. That'll take another 20 minutes or so. And then I want to tell you, what the theorems are, the actual uniqueness theorems are under what these assumptions are. And you'll see that, things look nice. Things looks good when it comes to these uniqueness theorems I'm going to show you. They make sense. The results are nice, and we like them. But then we'll talk about these uniqueness theorems So these uniqueness theorems apply when you make certain assumptions, and then as you can imagine, these assumptions have to be justified. And the only justification we have is the third part of today, where I'll talk about how do we justify those earlier assumptions. And then, we'll go into why that's not acceptable. And then I'll give you some details as how these arguments go, how it goes. And then, I'll look at some questions for these theorems. And the linchpin for this kind of twist in the lecture, in the later part of the lecture, is that there's a certain theorem called Hawking's theorem, which is used, and it's actually so it's interesting. The story behind that theorem is interesting. So Hawking and Ellis is definitely the top 3 books ever written in general relativity. I mean, it was such an incredible achievement what they did. But the book is full of mistakes. Like now it's understood that the book is full of mistakes, and some of these mistakes weren't caught on for multiple decades. So it's kind of interesting. So we'll talk a little bit about what those so Hawking's theorem is this, we'll discuss it, but basically it's this idea that you can extend the symmetries once you assume that the thing is analytic and it already has some other symmetries. I mean, that's the short of it. And this theorem is at the backbone of everything that came after. And we'll talk about those assumptions, and but that'll be lecture 3. Lecture 3 will be, what's this theorem? What's the proof of this theorem? What's the correct proof of this theorem? And how do we get around this theorem? And then lecture 4 will actually look at what people have done in the modern times. And hopefully by the end of that, you'll see that we're not close to an actual satisfactory resolution of no hair. So yeah. And another thing I should say is that beyond the initial specification that I mentioned at the beginning, where I said that even the theorems I'm going to show you today are known not to hold when you have matter, unless it's Maxwell matter. So taking that aside, what happens in electrovacuum, so Einstein-Maxwell, is quite different from what happens in vacuum. I mean, essentially it's similar, but there's much more. There's charge creates a balancing force to gravity, and so the solution space is more complicated, and the things that can remain kind of unique and stationary are more diverse than pure vacuum. But because that story is a little complicated, and it would demand of me too much time to go into that story, I'm not going to talk too much about electrovacuum. The story is very interesting mathematically, but I just won't have time to go into the details. Okay, so we'll start in a couple of minutes.
So with electrovacuum, are you thinking Kerr-Newman plus cosmology constant or something more?
No, I'm even just thinking just Kerr-Newman. I'm just even thinking, yeah. But when you have charge, lots of things get introduced which don't happen in vacuum. Because you can have like 2 things that are just repulsed, like, if they're 2 charged at the same charge, but they're attracting gravity, but they're repulsing from electrostatic. And so that, the configurations are much more diverse and
So you're saying that within static, within the type D spacetimes, there's one set of, there's already complications. And if you relax type D, then there's no complications.
Yeah, I'm saying, yeah, that's right. I'm saying that basically we're going to be in vacuum for most of today. I'm saying that when there's matter, you shouldn't expect uniqueness to hold anyway. The only matter fields for which you can expect some uniqueness to hold is Einstein-Maxwell. But there, the story is actually subtle and complicated, and it would ask, a few more lectures to explain it. In fact, I think that one of the participants, Weinstein, G. Weinstein, has been one of the leaders in the whole classification picture when it comes to Einstein-Maxwell. So perhaps we can have because there is a G. Weinstein also in mathematics who's in physics who's worked on this, but maybe it's not the same. Einstein-Klein. Eric asked me a question. Do I know about Einstein-Klein-Gordon? Do I know about Einstein-Klein-Gordon? The answer is no, I don't know. I don't know Einstein-Klein-Gordon, sorry.
There also, I think, you can have static solutions with naked singularities.
Yeah, I mean, naked singularities also happen in electrostatic, but yeah, I think, Eric, I don't know about Einstein-Klein-Gordon, but my impression is that it's probably quite complicated. So Eric asks, if Einstein-Maxwell has a uniqueness theorem, it seems plausible that Einstein-Klein-Gordon does as well. So, naively, yes, but actually no, because Maxwell introduces more symmetries and it's more restrictive. So, this is also a problem, for instance, if you want to form trapped surfaces, say, dynamically, you've got to preserve a hierarchy. And when there's a Klein-Gordon field, you just don't have a factoring out of the terms that you have when you have Einstein-Maxwell, which allows you to propagate a certain hierarchy. I could imagine that something similar happens when it comes to these uniqueness theorems. But yeah, to be pondered further. Okay, so it's 5 minutes past now, and those were some kind of preliminary remarks. I think it's maybe time to just jump in. Okay, so let's jump in. Again, to everyone involved, please, interrupt me anytime you want. This is really meant to be for everyone's benefit. Okay. So today the plan is part 1, domain and value communication. Then also, definitions. What's a killing horizon? What does it mean to be rotating? Part 2 is going to be uniqueness theorems. What do we know when the spacetime is static? What do we know when it's stationary and axisymmetric? And then part 3, how do we justify that something is axisymmetric? Well, typically we use analyticity, and I'll define what analyticity means and why that's not a realistic assumption. Okay. That shouldn't surprise you too much. So this is the past, and then this is the future. And so they intersect in this region. Use a different color. This is then the DOC, domain of outer communication. I believe Robert Garrosh in his wit and ability to come up with good definitions was the first one to come up with this definition. Okay. So these theorems that I'll show later on, they're only ever about the dock. So they're only about saying that the outside, is Kerr or Schwarzschild, etc. So this is a key definition. So what is a killing horizon? So you have a null vector. You also have a null embedded hypersurface, and it's invariant under the flow of this null vector. So if you move points or subsets of this null hypersurface under the flow of this K, you're not changing the induced metric say on that subset. Just so you are interested in this definition, the reason why it's there is because the key theorem that we'll talk about at the end is a theorem that says that the event horizon, which is something global, is in fact a killing horizon. This will be like the critical piece of the argument that'll underpin everything, right? That something which is about symmetries, something which is about event horizons, they are actually the same under some set of assumptions.
Martin, on this, can you with this say anything about the expansion of the null vectors generating the killing horizon?
No, it could have different properties, so everything's allowed. Pretty much. I mean, I'll show you some extra specifications.
So it doesn't have to be a trapped surface?
No.
Okay.
I'll draw a picture for this one.
It would help if you would explain some of the terms that non-specialists do.
Oh, of course. That's what's coming. I just I can't speak and write. But I still want you to see definitions in real time, just so you understand how they connect. Reading a bunch of text from a slide is hard. Okay, so basically we'll do some examples, but the picture is this. You have a set S, it's codimension 2, so it's like a space-like sphere. It's like say an S2 in four-dimensional space-time. You have light or null geodesics, as I should say more correctly. Outgoing ones, you have outgoing past direction, outgoing future direction. Then you have ingoing. Right, so if I'm on the surface of if I'm on the Earth, I can shine it away from the Earth, or I can shine it into the Earth. Oh. Okay, so do you see how you have, now you see that you have 4 surfaces, right? You have 2 going up, 2 going down. Okay, so you say that a set is a bifurcate killing horizon simply if K, which is that vector field that we talked about, which was the vector field, the null vector field, it's a direction in which the null hypersurface doesn't change, invariant under the flow of this vector field. If K is 0 on a set of S like this, it's an embedded codimension 2 space slice submanifold, then we say that this whole thing is a bifurcate killing horizon. Now we'll do some examples. So for instance, in Kerr, the outside of Kerr, this is S. Okay, so that space-like 2 sphere is at the meeting of the future event horizon event and the past event horizon. The same picture holds in Schwarzschild. Then given, this is important, given a killing horizon, so a killing horizon, we say it is,
Wait a minute.
yeah.
You said K equal to 0.
Yeah.
So that's a trapped surface then?
No, it just means the vector vanishes, the vector field vanishes on that set.
Yeah.
Nothing about
Does it
trapping.
mean the area doesn't change?
No, not necessarily. You could have I mean, if it vanishes, it's instantaneously 0. So the area is instantaneously non-changing in the future or in the past direction.
Right.
So it's, you could say it's, yeah, it's in that sense.
It has to be, but then you're saying that the same property is satisfied throughout its future and past.
No, so the K itself can change. It's just that the induced metric, say on S, doesn't change. So the vector field can do all sorts of stuff. Well, I mean, it's constrained by being a killing horizon.
That's the thing, yeah.
But if K vanishes, then you're right that the expansion at that place has to vanish. So it's marginal. It's marginally out of trapped surface if you're taking a slice through S. So for instance, I'll give you an example. For instance, in Schwarzschild, right? If we go along this direction in Schwarzschild, sorry. If we go in this direction in Schwarzschild, yeah? then going along this direction looks like this thing, right? It looks like a well. Okay. The expansion of this guy in this direction, h equals 0. And the k, which is non-zero along here, when we take the null expansion and we label the surface by sigma, then we see that this is 0. So I'm gonna correct myself. So if it's a minimal surface where h is 0, then the null expansion is 0. I think I spoke incorrectly. If h is non-zero, and this k is 0 because it vanishes. Oh no, but this, okay, no. I see what I'm saying. So I'm sorry about that. It's the early morning. I'm getting confused. So this is the trace restricted on sigma. So that could be non-zero, even though. No, but k vanishes. No. So what I was saying was correct. Yeah, sorry. Okay. So this is 0 if k is 0, because k is identically 0. This in Schwarzschild along this direction is also 0. So that's an example of a marginally out-of-trap surface, which is also a bifurcate surface. A bifurcate surface need not be a marginally out-of-trap surface, because you can have h non-zero. Yeah, you can have h non-zero. This thing could be non-zero. In that sense, even if this guy is 0, this thing could be non-zero. Does that clarify?
I didn't get it fully, but it's all right. Yeah, go ahead.
So, I mean, it's important that you get it. So let's just make sure we're on the same page.
Everybody else got it, it's fine.
Yeah, no, but let's just make sure.
I've got it, it's fine.
So first of all, we always have to specify directions, right? So there's 4 directions, right?
Okay, good.
So there's 4 directions. So if this is invariant under the flow and k is 0, then varying the surface in this direction, if this is the k that aligns with, if we're saying the k is in this direction, then the area of this guy doesn't change, and it's marginally out of trap with respect to this direction. But I'm saying nothing about that direction or that direction. So it's not necessarily trapped, because trapped, remember, is both.
Yeah, to me it seems.
So this thing in the direction where k vanishes is 0. But it need not be, right?
Can you have the future null expansion to be 0 and the past null expansion
Not
to be
0, to me
positive?
Yeah.
Oh.
Yeah.
You need some discontinuities or something. Yeah.
Yeah, I mean, no, but you can have that. You can have this direction being. You can have this direction being non-zero. You can have this direction being non-zero. Are you saying? Are you talking about this direction?
Pointing, I have no problem. I would have thought if your outward pointing guy in the future is 0, so other guy will also be 0.
In this direction?
Yeah.
This guy?
I'm not sure which is connected to which, but
I think upwards is future time.
Yes.
Maybe the left top one is going inward, and so it's inward directed future. So along that you want your null combinations to also expand somehow. maybe it's the left one. I think I'm this one.
I think you should continue, Martin. Probably obvious to a lot of people online. And it might make sense as we see what you're going to do with this.
So this one is, so I mean, I still don't understand what the confusion was. There's definitely one direction in which it's 0. And if you take the inward pass pointing and the null vector field is smooth and everything is smooth, then that direction is 0, but the other directions may not be. Okay. Okay, so now rotation. So a killing horizon is non-rotating if it's generated by stationary killing field and rotating otherwise. So the stationary killing field is, remember, it's the field that in a neighborhood of infinity is time-like. So here the vector field is time-like. Okay. This could change. This vector field could become space-like as it crosses the event horizon. Okay. It could even be that in a neighborhood of the event horizon, which it is in particular in the case of Kerr. But if this arrow ends up moving like this as I go inside, so that it matches with the event horizon, and that, you know, this particular field is in fact the K that defines the killing horizon up here, right? If it is this null killing vector that generates the horizon, then it's called non-rotating. So for instance, in Kerr, you have 2 killing fields. You have an axial one, and you have a time-like one in infinity, which captures the fact that it's stationary in infinity. It's time-like. But as this killing field moves inwards, the cross terms with the angles make it change causal character. And that's what rotation is. It's the fact that it, you know, the fact that this changing of the causal character of the killing field doesn't end up being exactly null. If it ends up being exactly null, that's what happens, for instance, in Schwarzschild. Schwarzschild is not rotating. So this is the essence of that definition. The important thing about this is that it's defined with respect to a killing horizon. So if you ask me, this is an event horizon, is it rotating? This doesn't apply. It has to be a killing horizon before I can say anything, which sounds a little strange, but that's the way it is. Okay. By the way, you know, all these definitions, you should always think to yourself, what are they like in Kerr or Schwarzschild? And you can always ask that question. And if they're good definitions, they should capture at least the difference. So given a killing horizon, again, everything is with respect to a killing horizon. Let's say it's HK, so it's generated by vector field K. We define GKK, just define this direction, this scalar. Then the surface gravity which is different k of hk is just the derivative. Okay, so this vector field is null on this hypersurface. Okay, it's null, but it might be changing. It might be becoming time-like, or it might be becoming space-like, and the derivative of this gives you a right-hand side, and the coefficient of this right-hand side is what we say is what we call the surface gravity. And then there's another definition, which is to say, well, if this is generated, this is degenerate if this kappa is 0, and it's non-degenerate otherwise. So does anybody have a feeling for where this pops up in the Kerr family? Or say again?
Extremal black.
Yeah, exactly. So when a black hole is extremal, for instance, the surface gravity actually is 0. There was a question in the chat, so I should go to it. What do killing horizon? Beautiful. There was a question in the chat by Weinstein. So it's Gally Weinstein and not G Weinstein that I see in my references when I research this topic. But thank you for the question. So the question is, what do killing horizons have to do with event horizons? This is the whole subject of this talk. And it's what I said at the beginning, that the main, like, Hawking's main idea, proof of his theorem is incorrect, but that doesn't matter. That the idea of the theorem is that an event horizon in a stationary space-time, under some other assumptions, ends up being a killing horizon. So to answer your question, they have nothing to do with each other. But when you have a stationary killing vector field and some other assumptions, they happen to be the same thing. We'll see why that's so important.
Martin, I have another question.
Yeah.
If you had a killing surface, which is not a killing horizon, just a surface where GTD goes to 0, for example, could you define then a surface gravity of that killing surface? You not correspond to null geodesics or something, but is that a meaningful thing to do?
So what's the null surface here? Sorry.
There is no null surface.
Okay. Well, what's the definition? What are you trying to say?
So locations where GKK goes to 0.
Okay.
K is a stationary killing vector field. These are killing
okay.
surfaces.
Okay.
They need not be null.
Okay. Okay.
So,
these are space-like guys where K is null,
right,
and K comes from a stationary guy.
right.
Okay. Yeah. And the question is,
so, like, for example, ergo surfaces, or for example, when you have naked singularities, the singularity itself has this property. Like at G, like the center of space, you have this property. So would you be able to, is it meaningful to define something called surface gravity there, associated to, say, some sort of time-like vectors, time-like geodesics, the expansion of time-like geodesics?
So typically when it's not a killing one, this the derivative of GKK is not proportional to K. So this right-hand side would have extra terms, and then it's not clear that you can just put a single coefficient in front of everything. So maybe someone has come up with a definition that applies in some cases and that generalizes it suitably. But then it's slightly different from this particular object. There's a question in the chat. Bifurcate killing horizon and black hole laws. I don't know what that has. Yeah, I mean, that's I don't know what Weinstein's comments there mean, but okay. Okay, so we can also say that it's mean non-degenerate if this is the kind of mean kappa, and this guy is coefficient of metric in Gaussian null coordinates.
Is there a classification which is when killing vectors and horizons correspond, and then different ways that they misalign?
Yeah,
So, yeah.
totally. Yeah. Absolutely. Yeah, we'll see exactly that. I mean, so we're actually going a little slower than I had hoped, but that's okay. Okay, so given that we're going a little slower, let me jump in right to the main classification theorems. So first main important theorem. This is the uniqueness of Schwarzschild. So what does this theorem say? It says that if the spacetime is smooth, if it's vacuum, if it satisfies some nice global conditions, like asymptotically flat, nice conformal infinity, nice event horizon, all the rest of it, and you have a complete static killing vector field. Killing field. Complete means that the orbits in the dock, it's non-vanishing in the dock, right? Then what do these imply? The dock is isometric to Schwarzschild. So this is a very nice theorem because the left-hand side they're all nice assumptions. Smooth is perfectly acceptable. Vacuum is perfectly fine. Global conditions, well, we expect those to hold in lots of cases, and we wouldn't even think of trying to prove these theorems if that wasn't the case. And the complete static killing vector field is basically as good as a symmetry as we can imagine. It means you have a time-like guy, it's stationary to infinity, but on top of that, it's hypersurface orthogonal, which means that it, essentially the derivatives of k, wedge k is equal to 0, also equivalent to integrability, etc., etc. So how the proof goes, yeah.
Minkowski is considered a subset of Schwarzschild.
Yeah.
So it satisfies it.
Yeah.
And Schwarzschild with a negative mass is also fine.
No, because that doesn't satisfy the nice global conditions. No, because in Schwarzschild negative mass, you have naked singularity.
Yeah.
So it doesn't satisfy
What does it not satisfy?
the global conditions. The global conditions involve some predictability assumption, globally hyperbolic, etc., etc.
Okay. Event horizon is also apparently something that
You're not assuming event horizon.
Yeah, no, I am. Event horizon.
So therefore, Minkowski is not counted or not?
It's counted in all the other assumptions, but it doesn't have an event horizon.
Okay.
Yeah.
Okay. Okay.
But even if I didn't assume specifically an event horizon, I'm assuming that the dock is globally hyperbolic. Okay, this is being assumed all the time. Otherwise, none of these theorems make sense. You can't prove any of these theorems. So dock has Cauchy surface. Negative mass Schwarzschild does not have that. Negative mass Schwarzschild has a naked singularity in the middle, and nothing is globally hyperbolic here. All right, there's naked singularities all the way down here. You got cones like this, where so that's ruling out negative mass Schwarzschild. The
zero mass is still all right.
Zero mass is still all right. It doesn't have an event horizon, but the dock there's certainly future null infinity, past null infinity, and certainly globally hyperbolic.
Okay.
Yeah.
So that's kind of an edge case.
Edge case, correct. Yeah, edge case.
Sam has a question.
Sam has a question. Is there a simple relationship between this theorem and Birkhoff's theorem? Yes. So the way you proved it is using Birkhoff's theorem. So what happens is that this complete in short, this is a kind of a gross explanation, but the complete starting killing vector field allows you to basically quotient out the equations. So you can just use the symmetries. They impose such a strong condition on the field equations that you can quotient out the field equations into a set of essentially elliptic equations. You lose the hyperbolicity because the time direction essentially kills any kind of variation in time, this complete starting vector field. And as a result of that, you end up with elliptic equations, and then you have to show that somehow they're spherically symmetric. And then you use Birkhoff's theorem to finish the proof. So yeah, it's totally related. It's a step in the proof. Does that answer? I hope that answers the question. Okay, so what I'm trying to convince you here is that when you're static, the uniqueness theorem is really nice, right? It's very clear, right? There's no issue. Now, this is the theorem for so this is uniqueness of Schwarzschild. This is uniqueness of Kerr under axisymmetry and stationarity. Okay. So this is the following theorem. It says LG is smooth, vacuum, global assumptions that are a little bit stronger than the ones above. Just the little bit stronger is just something about the generators of the event horizon. So you want them to and then here you have stationary and axisymmetric. Then your curve. Okay, so this is a very nice theorem. There's no problem with the assumptions. Everything looks good. You're basically just saying there's lots of symmetries. Axisymmetric, we saw that last time. It means you're invariant under SO2. It means that the fixed point of this orbit of the group is non-empty. So you have an axis of symmetry. And the way that the proof goes for this one is that the way the proof works is that first, so remarks on proof. So first, you show that global star plus vacuum and smooth implies very nice properties. So smoothness of event horizon, R cross S2 connected components of the event horizon. And then there is a little bit of black magic, not in the sense that it's wrong, but just in the sense that it's surprising. So you have this, you have the stationary killing vector field. Okay, you have the axisymmetric one. So let's say it's generated by M, and then it's asymptotically flat. And then that actually implies that these guys commute. And if you remember, this means that when they commute, this means that they're stationary and axisymmetric. So, sorry, I should have wrote this differently. You're stationary and axisymmetric. the way I defined it last time was that there's something called stationary, there's something called axisymmetric, but something that's called stationary and axisymmetric is an additional statement about the fact that these guys commute. Okay. And then what that does is that the commutation of these.
So there are examples where they don't commute.
Yeah.
Okay.
Yeah.
Because I grew up thinking they're the same. So
Yeah, no, there are examples where they don't commute. I don't know off the top of my head. I can't give you one, but yeah.
That is non-circular space-time, which.
Yeah. So when these guys commute plus vacuum equations, then you can show that the Einstein equations, so Einstein field equations, reduce to a boundary value problem. Boundary value problem. And then you study solution space of these guys. So let's call this star. You study solution space of star, and you end up with Kerr. So step D is actually the hard step. Like all these other, I mean, step A is pretty hard, and that was actually done in the 2000s and 2010s. The old theorems just assumed that you had nice components. Like for instance, Hawking and Ellis and Robinson and Carter, all these people, they would just assume that everything's fine. You're smooth event horizon, et cetera, et cetera. So that stuff's pretty recent, step A. Step B is Carter. So this was a magical insight. Step C is also Carter. Same time. But then this guy, this step D, is like Robinson 75, and then other proofs later on. And this is actually really difficult. So step D involves this magical identity that Robinson just somehow found by doing loads of computations. We won't go into that. I won't explain the proof, but basically that's how the proof goes. And if we go back to the static case, then the proof is the same. So you still have A, except that, oh, and then B is now even stronger because you have something that's, static. So the steps B and C reduce the problem to an even more rigid boundary value problem. And the equivalent of step D goes via Birkhoff's theorem, showing that you're spherically symmetric. And that was done first by Israel and done later by other people later under some preferential assumptions. So Israel, for instance, did it under some extra assumptions, but yeah. So there's questions in the chat. Okay, so this looks kind of interesting, but I'm kind of have to plow on, I'm afraid, or maybe we can come back to these. Okay, so any questions at this point before we talk about any questions at this point?
So what is questionable?
Nothing.
These are fine.
These are great.
Okay.
Yeah.
Okay.
So the whole point of today was to tell you that if you have symmetries, you're hunky-dory. No problem. The point is, how do you justify those symmetries? How do you justify that something's axisymmetric? That's where the problem goes. That's where analyticity and Hawking and all the rest of it, that's where things start to stink. Okay? But the point is, when you have these symmetries, in particular, when you say something is axisymmetric, you essentially just kill the freedom, you quotient everything, and then you can solve it under a smoothness assumption without having to assume something very strong.
So these are symmetries prior to Kerr?
What does prior mean?
I mean,
this is satisfied in Kerr, it's satisfied in Schwarzschild.
you can't have Kerr without axial symmetry, can you?
That's right. Yeah. So axial symmetry is axisymmetric is definitely a symmetry. Yeah.
So you're asking what are the symmetries that are explicitly or implicitly called for by starting with Kerr? Is that the question? Or are you asking before we even get to assume Kerr, there are certain symmetries which we want to justify?
That's right. That's right. Yes, it's the latter. So the point is to say, you want to classify stationary vacuum smooth solutions with nice global properties, right? Now I'm telling you that problem is totally unsolved, and we'll see in lecture 3 and lecture 4 why it's totally unsolved. However, you could say, okay, well, forget that problem. Just assume from the get-go that you're stationary, global, nice, smooth, everything, and you have axisymmetry. You have an axis of rotation, and everything is nice, you know, in the sense that you really have this SO2 that's acting on the space-time. Then you can just prove it's curved. And there's no problem. You can just do it. Like, I mean, it's not easy. That's why this led to nice papers and stuff. But, you know, this is a nice theorem. It's saying if you have these symmetries, you have curve. Now the question is, can we prove those symmetries happen? Can we prove they exist?
Yeah, I think this is where I'll come back to my earlier question.
Yeah.
I want to understand what is a space-time that is stationary but not axisymmetric. I would like to see, I mean, not today, but
Yeah.
an explicit space-time.
Yeah, there are loads, by the way. There are loads.
So
Yeah.
I like one.
Yeah, sure.
And then I
Sure.
can try to visualize why that guy doesn't have a black hole, a unique black hole.
Got it. Yeah, we can we can absolutely do that. Bear in mind though that, you know, it's still an open question. You know, it's still believed by some that. So when I said there are loads, that's you know, that's incorrect. I mean, there are none that we know. There are loads if you drop the other assumptions, but there are none if you have all the other assumptions. So for instance, if you have all of these assumptions apart from axisymmetry,
yeah,
and you want to prove that they imply axisymmetry,
yeah,
then you've solved the whole problem, right? So we don't know how to do that. So we don't, if we had counterexamples like you're asking,
yeah,
we don't have them.
Yeah.
What I can give you is if you drop the other assumptions. But if you know you're asking the right question. You want to say, do these assumptions, do they imply this assumption? Yeah.
show me one case where it's not.
No, but we don't have any.
Exactly.
We don't have any. This is the $1 million question, right?
Fine. I've understood the question in my language. Okay.
You're asking the right question. What I'm telling you is if you drop any one of these, then no problem. Okay, we have 10 minutes, but we also have a Zoom conference and I'm introducing the speaker. So I think, you know, we still have lots of things to do. So I think we'll do 5 minutes now.
You were going to say something about analyticity.
Yeah, but I don't.
Why did you make those comments at least so that I know what's the deal?
Yeah, all right. I'll make those comments. But I won't. So I'll make those comments, but I won't give you the examples I wanted to show you. I mean, do we have time? Yeah, I'll just show you the theorem. I'll show you the theorem because I think it's useful, and then we can discuss it. So this is like the theorem. This is like.
Close the chat window.
Yeah. So the theorem says, this is like the analyticity theorem. So this says, my assumptions are now going to be as follows. So analytic, vacuum, global, with some extra strong conditions, stationary, and then connected event horizon, and then either rotating or mean non-degenerate. Then you have to be Kerr. Okay. And the problem here is this guy. And basically, so just I'll define it next time with examples because I think it's going to be really helpful for you to see why it's such a problem. But analytic functions are functions that approximate.
Always.
So analytic.
So when you say analytic, so what exactly is it?
Yeah, exactly. So that's I mean, next time I'll give you lots of examples. You'll get a feel for it and everything. A real analytic function is one that is smooth and it's such that its Taylor series at any point converges to the function in a neighborhood of any point in that domain. So I'll give you, I mean, next time I really wanted to spend a lot of time so we see how crazy this assumption is, but basically like this.
Is it the metric that's going to...
This is not analytic, right? This is not analytic because if say this is like x equals 0, oh sorry, x equals say -1, and x is equal to 1, and the function is like say e to the 1 minus x squared, say, then when x goes to 1, this is 1 over 1 minus 1, 1 over 0, infinity, e to the minus infinity 0. And then if I define the function to be 0 outside, right, then this thing is infinitely differentiable. I can differentiate as many times as I want, but it's not analytic because at this point here, it's not analytic in 2 points. Here, because here the Taylor series is 0 because the function is 0, right? So this is for x.
Martin, I caused this problem by asking you to say more about what you meant
Yeah.
by analyticity.
Yeah.
But Jesse is tapping me on the shoulder saying
Yeah.
you have to get ready.
Okay, let me just finish with 1 minute. Just give me 1 or 2 minutes because I think this is important. So you've just come for the punchlines. It's fine. It's fine. All good. So today, what did we find out? We found out that if you have staticity, you're Schwarzschild. We found out that if you're stationary and axisymmetric, you're Kerr. Now we have to justify why are you axisymmetric? And this was the $1 million question. And Ramesh correctly asked the question, give me an example of something that satisfies all the above and not axisymmetry. We don't know of any examples. If we did, we would have solved no hair. We would have had these non-Kerr solutions. So how do we prove that we get axisymmetry?
For free, right? Basically, that's what we think. That if you make the other assumptions, axisymmetry will be automatic. Exactly. But it hasn't been proved.
It hasn't been proved. The only place where it's been proved is under analyticity. Okay? This is this theorem, analyticity. It tells you that if you're all of these guys, plus these extra assumptions that weren't in the other guys, then you're Kerr. And so next time, next time we'll do this theorem and we'll do what's left.
Thank you, Mark.
Thank you.
Recording, yeah.
Now I've got the thread of where we are going.